Come on. There we go. All right. So, good afternoon. Almost did it again. Nearly did it again. It's afternoon. It's the only class that's in the afternoon. Good afternoon. This is Precalculus A4. This is April 28th. Hopefully, you're all having a fantastic Tuesday. No better way to end the Tuesday than with some pre-calc. Today, what I'd like to do with you today is hopefully you're not freaking out by looking at the title of the lesson called Proving Trigonometric Identities. And you see over on the right-hand side, proofs with trig IDs. It's the forbidden P word in math of proofs. But yes, we're tackling some proofs today. In my opinion, I actually think that the proofs are marginally easier than the actual simplification problems that you've been doing all along the way, because they actually do give you some direction or some goals to aim for. In other words, you're trying to show that one thing is equal to something else. So it almost like it gives you an endpoint to work towards. Whereas just with the straight simplification problem, sometimes it's a little tough to figure out like where you're going or where your endpoint is. How do you know when to stop? How do you know if something's fully simplified? It's sometimes a little tricky to get past that, and that's why those simplification problems really do just require a lot of practice. But with proofs, it actually does give you a directive to work towards. It's like, hey, we want to get this side of the equation to look like this. So we're going to be working towards all of the steps possible to make that occur. All right, so we'll get to that in just a little bit. In the meantime, I just want to remind you that make sure that your microphones are muted and your webcams are off, which they all are, which is fantastic. Also, make sure you fill out the attendance form on Google Classroom. Hopefully, the progress assessment went well. Your grades are in Aspen. The answer keys are posted on Classroom. Overall, it seemed to go pretty well, so I was happy with that. If you do have any questions, though, after looking at the answer keys, and by the way, there were 2 versions of the progress assessment, so you should be able to identify which version that you had based on the questions. But I wanted to upload both of them for everybody so that if you didn't even have the other version, you could at least see the other problems and just get more exposure to more examples. But in any case, if you still have a question after looking at the answer key and after looking at your grade, or you just want me to go over more problems in greater detail, I'm happy to do that with you at any time during my scheduled office hours. So just send me a Google Hangouts message, or just email me, or let me know. Say, hey, Mr. Giorgio, can we meet at such and such a time? Or if it's one of those days like those Friday student intervention days, you could just say, because I'm at my computer all day, you could just send me a Hangouts message and say, hey, do you mind popping in the Google Meet for a quick minute? I have a quick question. No problem. I'll be right there and we'll work it out. All right. So that being said, what we're now going to do is we're going to be working with proofs. Yes, proving trigonometric identities, which is exciting. Rather than just, random sort of simplification problems, now we're actually going to work towards a goal. We're still going to use our identities that are all listed right below me, the quotient identities, reciprocal identities, Pythagorean, and cofunction. But now it's going to be a little more directed. So with these proof problems, right, the goal of these problems is that we're really going to try to show that both sides of an equation or any particular identity are equivalent. All of the identities below me, like the Pythagorean identities, the cofunctions, those have all been proven to you in this class. Yes, in a more abbreviated way than I may normally do it, but we've proven that sine squared plus cosine squared is equal to 1. We've proven that 1 plus cotangent squared is equal to cosecant squared. So what we're going to do now is just extend that to prove a whole bunch of things. All right. So our goal here is we're really trying to show that both sides of an equation are equivalent. Okay, that's what we're really trying to show. That's the goal of these proof problems. I'm going to give you an equation, and you have to show that both sides of the equation are the same. You can accomplish that in 1 or 2 ways, and the 2 ways are pretty interchangeable. You could either show that the left-hand side equals the right-hand side, or I'm sure you could figure out what the other way is. You could also show that the right-hand side equals, it's a sloppy looking S, equals the left-hand side. Okay? So a couple different ways that you could actually do this. Again, you could show that the left-hand side is equal to the right, or you could show that the right-hand side is equal to the left. Okay? Let me actually walk you through a good example now as to how we can do that. All right, so just a quick example. What if I asked you to prove that 1 over 1 minus sine squared of x is the same as 1 plus tangent squared of x? Okay, I asked you to prove that that's true. Well, again, you can do this in one of two ways. You could show that the left-hand side, this stuff, simplifies out to be this, or conversely, you could show that the right-hand side simplifies to equal this. Okay, you do not have to do both ways. You don't have to show one way and the other way. You could pick whichever way you want to do it. Typically, with a lot of proof problems that you'll see, it'll be fairly obvious as to which side you want to work with and which side you want to leave alone. Typically, the side that has more stuff going on, more complicated terms there, those are the terms that you want to manipulate and change versus a side that's a little more simple. But that being said, with a problem like this, I'll actually show you. You could start on the left, work with the left, and show that it equals the right, and that's sufficient for a proof. Or you could start on the right, work with that, show that it equals the left. So suppose that we start with the left side. In order to notate that, what we write is I usually write LHS, that abbreviates for left-hand side, just to show that I'm working with the left-hand side. So I'm not touching the right. This is actually my goal. I'm aiming to make this expression look like this. Okay, so working with the left-hand side, what I can do is looking at 1 minus sine squared of x in the denominator of that fraction, we could actually say, ooh, well, according to my Pythagorean identities, 1 minus sine squared x is the same as cosine squared of x, right? So I can rewrite that left-hand side as 1 over cosine squared of x. Okay? We're trying to, again, make it look like this. Now, 1 over cosine squared, hopefully you're thinking to yourself, ooh, that looks like a reciprocal identity to me. And if you look there, 1 over cosine squared, well, that's going to be the same as secant squared. So I can rewrite that now as secant squared of x. Now, we want secant squared to look like that. Luckily for us, there's a lovely Pythagorean identity that can help us out with that. If you notice, the secant squared of x is the same as the tangent squared of x plus 1. So we can go ahead and rewrite secant squared as tangent squared of x plus 1, which is equal to the right-hand side. Correct? We've now shown that this is tangent squared plus 1, and this is tangent squared plus 1. So, therefore, we've proven that this is equal to this. Okay? Remember, don't forget the very important part of a proof. You need that proof signature, right? In college, I was always trained to do a little box that you color in, but I like my personal proof signature, a little Triforce. But hey, you could pick whatever signature works out for you. I know you had those proof signatures way back in quarter 1 when you developed your proof signature. You got to stick to it, though. Once you have a proof signature, you can't be changing it. So, very important, though, that you include that little proof signature. But that's exactly how it's done right there. All right? Now, instead of starting on the left and working with the left, you could have actually done this problem by starting on the right and manipulating this to make it look like this. I'll show you what that looks like as well. Okay? So, little abbreviation of RHS, standing for right-hand side. That just means that we're going to work with the right-hand side of an equation. Typically, it's beneficial to write this down just so I know, and maybe even you know, which side of the equation you're working with, right? So I write RHS to signify that I'm going to be working with only the right-hand side, and I'm going to make this try to look like this. Okay, that's the goal. So what I can do is really just the same steps that we did here, but in reverse. 1 plus the tangent squared of x, that's a Pythagorean identity down there. We can rewrite that as the secant squared of x. Well, since we have a fraction over here, it's probably beneficial that we're going to need some sort of fraction over there. Using my reciprocal identity, I could write this as 1 over the cosine squared of x. That's the same as that. Now, cosine squared, well, look at your Pythagorean identity. You could manipulate that first equation of sine squared plus cosine squared is equal to 1 by subtracting sine squared from both sides, and you'd get that cosine squared is equal to 1 minus sine squared. Okay? that now is the same as the left-hand side, and therefore we've proven that this is exactly the same as this, so we're all good. Okay, you can do whatever proof signature you want. All right. Does that make sense to everybody how that works? Okay. Hopefully no questions. If you do have a question though, please feel free to type in the chat or let me know somehow. All right. Let's do a couple of examples just so you see how these proofs kind of work out. All right. Kind of the same idea where we're just using the trig identities, but now, like I said, we're working towards a goal. And that's why I think that proofs are actually a little easier, believe it or not. I know it's a tough thing to claim that proofs are easier, not implying that it's easy, but just saying that it's a little simpler than just straight simplifying, because you at least have something to work towards. Okay, maybe that's just because I'm all excited because I get excited about math easily. That's fair. I am a big math nerd, but hey, I hope that I can impart some wisdom on you as far as proving these things goes. All right, here we go. How about something like the tangent of x times the sine of x plus the cosine of x is equal to the secant of x. I want to prove that that's true. Okay, I want to prove that that's true. Now, if you're thinking to yourself, which side of the equation should I start working with? Should I manipulate the right-hand side to make it look like the left, or should I manipulate the left-hand side to make it look like the right? Well, I would definitely think to myself, let's start on the left-hand side. There's a lot more to do on that side. Here on the right-hand side, think about if you started here. You might be like, well, I could write secant as 1 over cosine, and then that's kind of it. Like, then you'd have to kind of be very creative with what you're doing going forward. You kind of run out of stuff to do. So definitely beneficial here to work with the left-hand side and try to simplify it down to the right. Typically, you want to start with the side of the equation that just has more going on. Okay, so what I could do is something like this. Let's see. Well, it looks like I could rewrite everything in terms of sine and cosine. So we could rewrite that left-hand side as tangent is sine of x over cosine of x. That's our reciprocal identity times, our quotient identity times the sine of x plus cosine of x. We can combine all this over here. We have sine, this is really over 1, so we have sine squared of x, that's sine of x times sine of x over cosine of x plus cosine of x. Okay? What we should be doing now is, in order to stick these things together, I need a common denominator for both of these fractions. The least common denominator we're aiming for here is the cosine of x, right? I'd like both denominators to be cosine so that I can merge these fractions together. In order to make that happen, I need to take this one and multiply by cosine over cosine, like that. So this is now going to look like sine squared of x over cosine of x plus cosine squared of x also over cosine of x. You probably see where we're going here, and I think it also helps to see the goal. Maybe you could start to visualize it even in your mind. Move this over here. We can merge these fractions together since they share a common denominator to make sine squared of x plus cosine squared of x all over cosine of x. There's our best friend Pythagorean identity right there. Sine squared of x plus cosine squared of x. Well, that's just 1. So this comes out to be now 1 over cosine of x. And we can rewrite 1 over cosine of x using the reciprocal identity as the secant of x. And we've now shown that that's the same as the right-hand side of the equation. Secant of x is the same as secant, obviously. So we're done. Okay? We've successfully proven that. Hopefully you see a couple things. Hopefully you see why it's beneficial to have this goal to work towards. Personally, when I started working through this problem, I started visualizing the end right about here, where I was like, oh, these are going to combine. This is going to be 1 over cosine, which is secant. Okay? And so it's helpful to be able to see that goal all along the way. Other big takeaway here is hopefully you can recognize why it's beneficial to choose to start on the left-hand side first, because there's just more to do. All right? So by manipulating that, we get to secant. Now, let's try another problem. How about something like this? We got a couple, how much time do we have? We have 15 minutes to go. That's plenty of time for some more proofs. Let's prove that the tangent squared of theta is equal to the cosecant squared of theta times the tangent squared of theta minus 1. Okay. We're going to try to prove that expression. Which side of the equation do you want to start on? Again, I would look at a problem like that and I'd say there's a lot more going on the right. On the left, yes, I could change tangent squared to secant squared minus 1, and then we're kind of run out of stuff to do. So let's work with the right-hand side, and let's see if we can make this expression look like this. So let's work with the right-hand side. Okay. What I can do is I could rewrite everything in terms of sine and cosine. That'll probably help. Notice you may be tempted to do tangent squared minus 1 and write that as some variation of secant, but we can't actually split these up because these are glued together, right? Actually, it's cosecant minus 1, that's cotangent, but we can't split these up because these two terms are actually stuck together. So we just have to try to change it to sine and cosine. So I can rewrite the right-hand side as 1 over sine squared of theta times, well, tangent squared is sine squared of theta over cosine squared of theta, and then minus 1. Hopefully you see the little advantage of doing that now is we have, sine squared over sine squared. That's going to go away. We can now rewrite the left-hand side, or sorry, the right-hand side as 1 over cosine squared of theta minus 1. Okay. A common mistake a lot of students do, please do not do this. A lot of people are tempted to do 1 minus 1 is 0, and then you have 0 over cosine squared, which is 0, and then they put a big question mark because they don't know what to do. Make sure you don't do that. This is one term that stays together. This is a term that stays together. Okay. Well, how can I rewrite 1 over cosine squared? Well, I could rewrite 1 over cosine squared now as secant squared of theta minus 1, because remember, we're aiming for this tangent squared of theta, and now you could recognize, Pythagorean identity, secant, it's the last one written on the third line written on my little sidebar there, secant squared of theta minus 1 is the same as the tangent squared of theta. By a little Pythagorean identity, that's the same as the left-hand side of our equation, and so we've proven what needs to be proven. Okay? Question about how that's done. I do want to emphasize as I'm going through these problems, there are a lot of different ways to do them. This is only one specific way that I am showing you. It doesn't mean that there aren't other avenues that you could take to arrive at a final answer. For example, in a problem like this, could you get a common denominator of cosine squared? Probably. If you did a common denominator of cosine squared, you'd rewrite this as cosine squared over cosine squared. You could then stick these together. You'd get sine squared over cosine squared, which becomes tangent squared. Hopefully you see what let me write it so you see what I'm talking about. So at this point, you could have said, well, if I want to make a common denominator, we could do this. Now we could stick them together. Now 1 minus cosine squared is sine squared, and that's the same as tangent squared. See that? So there's a lot of different avenues that you could actually go through in order to get these problems. I'm just showing you one possible route that you could take. Okay? So there are some dead ends. I'm not going to kid you about that. There are certainly some areas where you could try to go down and you might be like, oh, this isn't really getting me towards my goal. So you may want to turn around. But that's okay. That's okay. We'll just try again. Let's do another one. Okay? Let's do another one. How about this? Let's prove that the cotangent squared of theta over the cosine squared of theta minus 1 is equal to the cotangent squared of theta. Okay? Let's try to prove that. The question is always, what side of the equation do you want to work with? Here, I think I definitely want to work with the left-hand side because there's, again, just more to do. Cotangent squared, I could write that as cosecant squared minus 1. Then there's not much else to do, right? You kind of get stuck, or you'd have to be very, very creative in order to take something like that and make it look like this. So a lot more to do to simplify the left-hand side and make it look like the right. Let's get going. Let's see. Probably beneficial to write this all in terms of sine and cosine. So I could rewrite cotangent squared as cosine squared theta over sine squared theta, and that's all divided by cosine squared of theta. And we have this minus 1 stuck over here. Well, if I'm taking this whole fraction and dividing it by cosine squared of theta, that's really the same as taking this whole fraction and multiplying it by 1 over cosine squared of theta, right? It's just like dividing by 2 is the same as multiplying it by 1/2. It's beneficial to write it out that way because then, take a look. Take a look. Cosine squared over sine squared times 1 over cosine squared minus 1. By writing it out this way, you can see, ooh, cosine squared theta is going to cancel out. And now I'm left with 1 over sine squared of theta minus 1. Let me just go through that step one more time. What I did here, I have a fraction divided by cosine squared. So instead of writing it this way, I just rewrote it as it's the fraction times 1 over cosine squared. Right? It's the same as saying divide by cosine or multiply by 1 over cosine. The cosine squareds cancel out. That's why I think it's nice to write it that way, because that cancellation becomes clearer. You're left with 1 over sine squared of theta minus 1. Again, a tempting mistake is to do 1 minus 1. This is a completely separate term. Please don't touch it. 1 over sine squared, though, we can now write as the cosecant squared of theta. Very similar to the problem up here, actually. Minus 1. Well, that's just our Pythagorean identity. The cosecant squared of theta minus 1 is the cotangent squared of theta. See that middle Pythagorean identity right on the little sidebar below me? If you subtracted 1 from both sides, you would see cosecant squared theta minus 1 is equal to cotangent squared of theta. That's exactly what we were looking for on the right-hand side. And so our proof is done. Okay, we've accomplished the goal. Any questions about that at all? No questions? No
Mr.
comment.
Dojo.
Oh, we got a question. What's up?
Yeah, sorry. On the right side, it's cotangent squared, and then on the left, I'm confused about the minus 1 in the final answer.
The minus 1 right here?
No, in the final answer.
This here?
On the bottom. Yeah, because it's not equal to cotangent squared on the right.
It is, because if you notice, the middle Pythagorean identity, right, says 1 plus cotangent squared is cosecant, so subtract the 1 from both sides.
Okay, I misread that. I'm sorry.
No, no problem. Do you see what I'm talking about?
Yeah.
Good. No, I'm glad you brought that up. Great. Okay. Any other questions or anything? All right. Again, don't be afraid to interrupt. You can interrupt if you need to. That's why we're here for you. All right. Here we go. Let's do another one. A couple more. Okay. How about something like this? Let's prove. This one's a little trickier. How about the sine of theta plus the cosecant of theta, all divided by the cosecant of theta, is equal to the sine squared of theta plus 1. Okay? How about something like that? Well, which side of the equation would you actually want to work with here? Would you want to work with the left-hand side, or would you want to work with the right-hand side? And maybe it's not as clear in this problem which side you actually want to start on. So you could try to start on one side, and if it gets you somewhere, then that's great. And if it doesn't get you anywhere, then that's okay. You can just backtrack and start on the other side. Personally, in this problem, I would definitely start on the left-hand side and work with that to make it look like the right. But suppose, I just want to show you, suppose that you did start on the right-hand side, and you said, well, I could rewrite sine squared as 1 minus cosine squared, right? That's our Pythagorean identity. Then you'd have maybe 1 plus 1 is 2. So I'd have 2 minus cosine squared, and it doesn't seem like this is working towards here, though, right? So, you know, maybe we can work with that side, but it doesn't really seem to be getting me anywhere. Let's try to work with the other side. That's okay. It doesn't mean we have to panic and freak out and cry. It means, all right, we tried the right-hand side, just didn't really get anywhere. Let's see if we can instead work with the left-hand side and see if that gets us somewhere, okay? What I can do with these is I can go ahead and split up this fraction. I could rewrite this fraction as sine of theta over cosecant of theta plus cosecant of theta over itself. Right, that's equivalent. Now, cosecant of theta divided by cosecant of theta is just any number divided by itself is 1, which is nice. So I'm just going to rewrite this as sine of theta over cosecant of theta plus 1. Now, what we could do is we could say here, well, cosecant, right? Because again, we're trying to aim for sine squared of theta plus 1. So you might be like, oh, I got my plus 1. That's good. I don't want to touch this. I have it. That's what I want, and I got it. Let's try to make this look like sine squared. So in order to make that happen, we could say, well, cosecant of theta is 1 over sine. How do you divide by a fraction? Well, you just multiply by the reciprocal. We now have the sine of theta times the sine of theta over 1. That's multiplying by the reciprocal plus 1. And then hopefully here you can see that that's going to become sine squared of theta plus 1. And that's the same as my right-hand side, so I'm happy. Okay? Again, a big takeaway is don't get all bent out of shape if you decide, hey, I'm going to start working on the right-hand side and see if that gets me anywhere, and it doesn't. That's okay. That just means let's backtrack, let's put it on pause, let's try the left, and let's see if we can work with that to make it look like that. Okay? The other big takeaway I want to bring from this problem is the fact that we get the plus 1 here fairly early. And that's good because looking at your goal, you should be like, ooh, I have this plus 1 now. So now all I have to do is just make this part look like this part. So it kind of splits it up into smaller tasks when you see your goal in front of you. That's why I like proofs versus simplification problems. I mean, I like both. Let's be real. I'm not going to say I like one over the other. Everything's excellent. But I like these problems because they give you that directive to work towards. And I think that's a very important part about proofs. One more problem I have for you to end the day. How about something like this? This one's cool. I like this one a lot. How about the sine of x plus the cosine of x squared plus the sine of x minus the cosine of x squared is equal to 2. And I want you to prove that. Super cool. Obviously, we're going to start on the left-hand side. It's not really much we can do with just a regular old 2. Keep in mind, when you see something like this, this is the sine of x plus the cosine of x all squared. It's not the same as sine of x, sine squared of x plus cosine of squared x, right? It's the same as y. X plus y squared is not the same as x squared plus y squared. How do we square something? We have to multiply it by itself. When you see x plus y all squared, that's the same as doing x plus y multiplied by itself. And so you'd get x squared plus 2xy plus y squared, right? A little bit of first, outer, inner, last, which we, of course, call the distributive property. So that's exactly what we're going to do here. When I have sine of x plus the cosine of x all squared, that is not the same as sine squared of x plus cosine squared of x. It is the same, however, as sine of x plus cosine of x times itself, because that's what it means to square something, sine of x plus cosine of x. Okay? Same thing going on over here. We're going to square this, so we're going to multiply it by itself. Oh, and by the way, we're working with the left-hand side. Almost forgot to indicate that. Minus the cosine x times itself, sine of x minus cosine x. Okay? A little bit of first, outer, inner, last distributive property happening over here. We need sine of x times sine of x is sine squared of x. Sine of x times cosine of x is plus cosine x sine x. Cosine x times sine x is another cosine x sine x. Cosine x times cosine x is cosine squared of x. That's just a little first, outer, inner, last, just like we did over here. Okay? Don't freak out. It's going to be a lot of terms, but we'll get through it together. Okay? Now let's do this one right here. We have sine of x times sine of x is sine squared of x. Sine of x times negative cosine of x is minus cosine x sine x. Negative cosine x times sine x is another minus cosine x sine x. And then negative cosine of x times negative cosine of x is positive cosine squared of x. Again, you look at that and you're like, oh boy. But take a look. We have positive cosine x sine x, negative cosine x sine x. Goes away. We have the same thing again. Positive cosine x sine x, negative cosine x sine x. And look at what we have left after we simplify all of that fun stuff. we have sine squared of x plus cosine squared of x. That's this one and this one. Plus sine squared of x plus cosine squared of x again. That's this one and this one. And this is just our favorite Pythagorean identity presented to us twice. Sine squared plus cosine squared is 1. Sine squared plus cosine squared is again 1. And I get 1 plus 1, which is 2, the same as my right-hand side. And so I'm happy with that. Okay? Super cool, in my opinion, that one works out nicely. All right. Any other questions, comments, or concerns about this? All right, just to quickly wrap up, I am going to post some practice problems on Classroom very soon, probably within the next half hour. They'll be up there. The answer key will be provided as well, so you can feel free to check your work. I highly recommend that you do. It's not a graded assignment, but it will only be to your benefit to try them before Thursday's class. On Thursday's class, I'll probably go over a couple from those practice problems, and then I'll be happy to show you just more examples of proofs using the trig identities. After Thursday's class, we are going to get another graded assessment on the proofs. There's going to be 3 proofs, I think, so you'll just have to go through those, all right? If you do have any questions or concerns, though, please feel free to let me know. Other than that, I think I've said everything I need to say. I don't want to keep you for longer than I have to, so I appreciate your attention and focus on this Tuesday afternoon. I do hope you have a fantastic rest of your day, and stay safe, stay healthy. I'll see you guys on Thursday. Have a good day.